This lecture is on substitution versus elimination, Part A. SN1 versus E1 reaction. Unless a Lewis acid catalyst, for example aluminum chloride, helps to pull off the leaving group, tertiary alkyl halides do not perform substitution reactions in aprotic polar solvents. An aprotic polar solvent, remember, does not hydrogen bond. So for example, 2-chloro-2-methyl-propane, or terbutyl chloride, does not react with azide anion, N3-, in DMSO. DMSO is an aprotic polar solvent. There is no reaction because we don't have a Lewis acid catalyst helping to pull off the leaving group. Azide is incapable of reacting via SN2 because the tertiary alkyl group is too bulky. There's too many methyl groups in the way to allow the azide to come from the back and displace the leaving group. However, tertiary alkyl halides perform mostly substitution reactions with protopolar solvents as the only nucleophiles. So now if we go back to the 2-chloro-2-methyl-propane case, if we dissolve that in methanol, you see at the bottom, our major product obtained in good yield is 2-methoxy-2-methylpropane, the major product, and a minor product of 2-methylpropene. How does the reaction of 2-chloro-2-methylpropane and methanol work to form the major and minor products? Well, if you study the reaction rates at different temperatures, they'll let you calculate what's known as the entropy of activation, delta S dagger. Delta S dagger is negative for two molecules colliding in the rate determining step, such as an SN2 reaction. You're gathering two molecules together, so you have decreased your randomness. You have made the system more ordered, thus the entropy is negative. In the reaction above, the entropy of activation is positive for the formation of either organic product, whether you form the major or the minor product, meaning that there must be a step where 2-chloro-2-methylpropane breaks apart, dissociates. So the rate determining step for both reactions involves the breakup of the molecule 2-chloro-2-methylpropane. How does this breakup or dissociation of 2-chloro-2-methylpropane work? The protopolar solvent is essential. It develops hydrogen bonds to the leaving group, allowing it to break off. Dipole ion attraction stabilizes the resulting carbocation, that is a positively charged carbon. The following animation will show how the chloride is removed by methanol to form the carbocation. So we have two mechanisms that produce the products of the reaction of 2-chloro-2-methylpropane with methanol. The first mechanism is called SN1. That's our substitution reaction. The rate of this reaction is equal to K, the rate constant for SN1, times the concentration of our 2-chloro-2-methylpropane. SN1 stands for substitution nucleophilic first order. But you can see the rate of the reaction is first order in 2-chloro-2-methylpropane. The rate determining step is the loss of the chloride in our slow step to form our carbocation. That's the step in which the delta S dagger, the entropy of activation, becomes positive because we're forming more particles than what we started with. In the fast step, methanol with its lone pair attaches to the carbocation, forming a new CO bond. And in another fast step, chloride anion pulls off a proton to form our final product, 2-methoxy-2-methylpropane plus HCl. In the E1 reaction, we start the same way in terms of forming the carbocation. So the chloride group is removed. Again, that's because of the protopolar solvent yanking it off. That's our slow or rate determining step. forming our tertiary carbocation. In our second step, the chloride acts as a base to remove the proton and form a double bond. That's a fast step. We still get HCl as a product, but now we have an alkene. This is the E1 mechanism. The rate of this reaction is equal to the rate constant for E1 times the concentration of 2-chloro-2-methylpropane. Note that both SN1 and E1 have essentially the same rate expressions. They're only different based on the rate constant values. They both depend on the formation of the carbocation. So how do we know whether the substitution reaction SN1 or the elimination reaction E1 will be the major process? Well, it depends on the relative rates of the reactions. SN1 will be faster than E1 when only protic polar solvent is the nucleophile. There's nothing else. Or there's no beta hydrogen. That is, there's no hydrogen adjacent to the carbon that's going to become the carbocation. If there's no beta hydrogen, you can't make a double bond, so you can't have elimination. E1 will be faster than SN1 when another weak base is present with the protic polar solvent. And we're talking all sorts of weak bases. The definition of a weak base is it's not hydroxide, OH-, not an sp3 hybridized carbon connected to O-, or even stronger bases like the amide anion, Nr2-, or C- when it's alkyl, so that we're talking about things like CH3 or C single bonded to C, alkenyl, C double bond C, or alkynyl, C triple bond C. So an example shown below, there's our 2-chloro-2-methylpropane, again reacting in methanol as the protic polar solvent, but we've added the weak base acetate. That's now going to shift the reaction rate toward E1. So now E1 is going to be the major product and SN1 will be the minor product. Okay, now let's take a look at alkene stability and major E1 products. In many cases, an E1 reaction will yield more than one alkene. How do you know which alkene is the major product? Here's how it works. If more than one alkene product can form from an E1 reaction, the most substituted, most stable alkene will be the major product. That's known as Zaitsev's rule. So if you look at the example below, we have a tertiary alkyl chloride reacting with acetate anion as the weak base in acetic acid as the protic polar solvent. So this is an E1 reaction that forms two different products. The more substituted major product and the less substituted minor product. Note that in the major product, the carbon-carbon double bond is tri-substituted, whereas in the minor product, the carbon-carbon double bond is di-substituted. In the mechanism of this reaction, the chloride anion is removed by the protic polar solvent, forming our tertiary carbocation. The acetate anion then removes the beta hydrogen from one of two positions. In the A reaction, you form the minor product. In the B reaction, you form the major product. To figure out how to form carbocations, we need to look at carbocation stability. Both SN1 and E1 reactions require carbocation formation. Under non-acidic conditions, only tertiary and resonance-stabilized carbocations can form. So let's look at the stability chart for carbocations. The benzylic carbocation, we have a benzene ring attached to C+, is very stable. It's about as stable as a tertiary carbocation because of the resonance between that plus charge and the benzene ring. That's that empty orbital pi resonance. The tertiary carbocation is more stable than the secondary allylic carbocation, whose plus charge is adjacent to two carbons and whose plus charge can resonate into one carbon-carbon double bond. So it's not as good as a benzylic carbocation or a tertiary carbocation. We'll see in a moment why the tertiary carbocation has such significant stability when it doesn't have resonance. Now, the secondary allylic carbocation is much more stable than a simple secondary carbocation where there are only two carbons connected to the plus charge, or a primary allylic carbocation where there's only one carbon with a plus charge connected to a carbon-carbon double bond. So the resonance between the plus charge and the double bond allows for some resonance stabilization. Both these systems, the secondary and the primary allylic system, are really only practical in strong acids, or in the presence of a Lewis acid like aluminum chloride, which will pull off the leaving group leading to the carbocation. Under non-acidic conditions, we're really going to ignore these situations, in terms of any practical scenario. So we're going to focus on the benzylic, the tertiary, and the secondary allylic carbocations as reasonable carbocations to form in non-acidic conditions. The carbocations that are not at all possible are the primary and the methyl carbocations. Chemists have tried for decades to make these, and pretty much we consider them to be impossible. Now, why is it that the tertiary carbocation is so stable? There is an idea called hyperconjugation, the overlap of sigma bonds transiently parallel to the empty p orbital, that will stabilize the carbocation by donating electron density. So, if you think about the tertiary case, you have sigma bonds all around the carbocation's empty p orbital, able to slightly donate electron density. You see the little pulsing dotted lines into that empty p orbital, which makes it a little happier than if it were simply a sextet of electrons, and that makes the carbon feel like it has a little bit better than just 6 electrons. Not truly an octet, of course, but it's a little bit more stable than a simple sextet. So that hyperconjugation through the parallel overlap of sigma bonds and the empty p orbital stabilizes the carbocation, and the tertiary carbocation has more of that hyperconjugation than any other level of substituted carbocation. Practice problem 1. Predict the major product or products of each of the following reactions. In these cases, we're going to focus exclusively on SN1 versus E1. So there are no SN2 or E2 reactions in these examples. So make sure that you consider the conditions, a protic-polar solvent, and whether or not you have a weak base present to allow for E1. If there's no weak base present, then it's going to be an SN1 reaction. Don't forget that you're going to form a carbocation, so the nucleophile can react with either the front or the back of the carbocation. That may lead to more than one enantiomer if it's going to generate a stereogenic center. At this point, you want to pause the video in order for you to work on the practice problem. Answers to practice problem 1. In part A, we have a tertiary alkyl chloride and only the protic-polar solvent, water. So this is an SN1 reaction as the major mechanism. The chloride is replaced by OH. The other product, which is not shown, is HCl. In part B, the tertiary benzylic alkyl bromide is going to form a very stable carbocation under these conditions. Methanol is the protic-polar solvent. There is no other weak base, so this is an SN1 reaction. Since this tertiary benzylic compound is chiral, that means that when you form the two products, you're going to get a mixture of two enantiomers, a racemate, in which CH3O from methanol will combine to either the front or the back of the carbocation, and you'll also form HBr as the inorganic product. In part C, we have the same tertiary alkyl chloride we had in part A, but now acetic acid is our protic-polar solvent and acetate anion is a weak base. This is going to lead mostly to E1. So now we have two possibilities. We have the double bond forming external to the ring, which would be less substituted than the major products shown, where the double bond is internal to the ring. That's a tri-substituted product. And remember, E1 always forms as the major product the most substituted, most stable alkene, which is what this one is. In part D, we have a repeat of the same substrate that we saw in part B, another chiral tertiary alkyl bromide that is benzylic. But now instead of just methanol, we have the weak base N3- azide anion. So the reaction transforms from mostly SN1 to mostly E1. The double bond forms in between the carbon with both the benzene ring and the methyl, and that carbon with the methyl group at the end. So that's going to give you a tri-substituted alkene. Again, by Seitzev's rule, the most stable product. Part E, we have a secondary allylic carbocation that can be formed. Tosylate is our leaving group. Our protic polar solvent is acetic acid. So replacement of tosylate by the acetic acid will not simply give us the product you might imagine, which is just the acetate attached to where the tosylate is. You have to look at this mechanistically because of resonance. If you remove the tosylate, the carbocation will resonate to form a trans disubstituted alkene with a carbocation on the end. That will then react with the acetic acid to form a protonated intermediate, which then, once it loses its proton, will become the desired most substituted, that is disubstituted, and most stable, that is trans alkene. Now, why didn't we look at the benzylic cases in terms of drawing resonance structures? We don't touch benzene rings in terms of actually attaching atoms to them. You can use benzene for resonance, but you can't actually break up the pi bonds in any permanent way to form a new bond to another atom, such as a nucleophile. So we're not really allowed to do that. Resonance stabilization with a benzene ring is great, but don't mess with the benzene ring. So in cases B and D, where we have the tertiary benzylic case, the benzene ring, the pH group, the phenyl group can stabilize the carbocation, but you cannot attach the nucleophile to the benzene ring, even though one can draw resonance structures that put plus charge in the benzene ring. Can't do it because it disrupts the very stable benzene ring structure. Practice problem 2. Draw the mechanism for each of the following reactions. We're still focusing on SN1 versus E1. At this point, you want to pause the video in order for you to work on the practice problem. Answers to practice problem 2. In part A, we have the loss of the chloride leaving group to form our tertiary resonance stabilized carbocation. Note the carbon-carbon double bond adjacent to the plus charge. So we have to draw a resonance structure other than the initial one, where that plus charge resonates to the bottom portion of the ring, and now that gives us two possible products. Okay, methanol can react with that carbocation at the tertiary position to form an intermediate that's positively charged, and then chloride can deprotonate that intermediate to form the final product, plus HCl, or by a resonance, the carbocation could be at a secondary position with the carbon-carbon double bond in the more substituted, tri-substituted position. Methanol attacks the carbocation, again forms the protonated intermediate, which is deprotonated by chloride to form the other product. Note that the SN1 products in part A are actually racemic. So we really get a pair of enantiomers for each. In part B, we have a tertiary alkyl bromide. Loss of the bromide will form a simple tertiary carbocation. Since phenoxide, the PHO- is a weak base, we know that because the benzene ring carbon is sp2 hybridized, not sp3. So an sp2 hybridized carbon connected to O- is a weak base. That will lead to the E1 mechanism. Phenoxide will deprotonate the beta hydrogen. The electrons will flow toward the carbocation, giving us our tetrasubstituted alkene product plus phenol, PHOH. Practice problem 3. Arrange the following carbocations from left to right as 1. Most stable to 4. Least stable, and explain. Remember, the most stable carbocations are tertiary and benzylic, and the least stable carbocations, which you can't even really form, are methyl and primary carbocations. At this point, you want to pause the video in order for you to work on the practice problem. Answer to practice problem 3. If you look at the first carbocation, it's tertiary. There are 3 carbons connected to the carbocation plus charge, and there's an adjacent carbon-carbon double bond. So that's tertiary and allylic. That seems pretty good. However, the one next to it is tertiary and benzylic. There's a benzene ring connected to the plus charge. Now remember, in our carbocation stability, the resonance to a benzene ring is more stabilizing than resonance to a simple carbon-carbon double bond. So since both of these are tertiary, but the second example is benzylic and the first example is allylic, the tertiary and benzylic example will be more stable. So that's number 1. And the first example is a little bit less stable, that's number 2. Now in the final 2 examples, you have a tertiary carbocation and a secondary carbocation. So these are fairly easy to order. The tertiary carbocation would be number 3, the most hyperconjugation, as compared to the secondary carbocation, which would be number 4.